Now we want to talk about rotational motion. And this is the type of motion that occurs when an object moves in a circle or a curve. And for our purposes, we're going to assume only circular, okay? So a few chapters ago, we looked at the example of a tennis ball tied to a string, and it traces out, its path traces out a circle here. And the motion that we're going to consider is exactly this. So instead of using position coordinates like x, where remember velocity is the change in distance over the change in time, or a change in your x position as a change in time, what we're going to consider is an angular unit of for position. Okay, so instead of x or y or distance, we're going to use an angular unit of position. So what we can think about is if I have a circle and I have an origin here, and I can even draw some axes through here. So here's my x-axis, here's my y-axis, and my origin is right here in the middle. And let's say that I have my object is sitting right here. Now it can only move along this circle, right? It can only move along that circle. And instead of giving it an x position here and a y position here, okay, what we typically tend to do is instead we measure it, we give it an angular measure from the x-axis, okay? So we basically say if I have a ray right here, or a line segment rather, right here, and then I displace that line segment upward, keeping it fixed at the origin, then my line segment is now right here, and it has gone through some angle. So my new line segment makes an angle with the x-axis, an angle of theta. Okay, so we use the Greek letter theta to denote the angle that two line segments make with respect to each other. So now theta is going to be our position coordinate. And something that you can ask is if the particle was here at time equals 0, and then it was up here at some later time, the question is, how fast did it move from here all the way up to here, right? How fast did that take place? So we can ask, what was the rate of the change in angular position? And in fact, the equivalent question to ask, or an equivalent question to this, is what is the angular velocity? Anytime we have the rate of change of a position, that's going to imply a velocity. And because now we're moving in angular quantities or angular displacements rather than linear displacements, we're going to give this the term angular velocity. And we're going to give it a special letter. It looks like a W, but it's in fact a Greek lowercase omega. And this is the angular velocity. Okay? And it literally is just how fast an object moves from one initial angle to the next initial angle, right? It's just how fast the object is going around the circle at a given particular instant, right? But mathematically, because it's the change in angular position, we write it as delta theta over t. Okay? So instead of using x or d for our position, we now have theta, and instead of using v for our velocity, we now have omega. And I should specify one thing here. Our circle has a specific radius, and that radius is r. Okay? Now, another question that you can ask is, what if the velocity is not constant? And something that might be akin to this is, say you have a tire that's rotating on your vehicle, and you are looking at a specific point on the rim, and if your car is going at 55 miles an hour, then that point on the rim is going to be going a uniform omega. But then what happens when you put on the brakes? It's going to slow down, and the angular velocity is going to change. There's going to be an angular, what we call an angular acceleration. So when the angular velocity starts to change by either speeding up or slowing down, we get an angular acceleration. Okay? And we denote that by the letter alpha. Right? And alpha is going to be the change in angular speed over time. Okay? So here we have our position, we have our velocity, and we have our angular acceleration. So these three variables now take the place of x and v and a. Right? But we have some simplifying physics that we can do here. So I'm going to split this up into two cases. The linear case, which is what we've been looking at so far. Oops. Linear and angular. And let's remind ourselves of some of our kinematic equations. The first equation that we really learned was the equation for velocity. And remember that the equation for velocity was distance over time. And another way to think of the term distance is the change in position of an object. And so in the angular form, we're going to have omega is equal to delta theta over t. We also saw that there's an acceleration equation, which is delta v over t. And we just saw that we're going to have alpha is delta omega over t. But we also had a few other equations. We had v final equals v initial plus at, and we had d is equal to vi t plus 1/2 at squared. And the question is, do these two equations have angular analogs just as these two equations do? And the answer is yes. All we have to do is substitute our values. Theta takes the place of our distances. So anytime you see a d or an x in any equations, you just replace that with theta. Anytime you have a v over here, as in vf or vi, just replace that with an omega. And anytime you have an acceleration, just replace that with alpha. Now I should specify this is for constant accelerations. Okay, these equations are only valid for constant accelerations, but under that condition, then this is purely perfectly fine to do. So we can have omega f is equal to omega initial plus alpha t, and delta theta is going to be equal to omega I t plus 1/2 alpha t squared. Okay? And this is perfectly applicable. All right? Now let's talk a little bit about the units. What is theta measured in? What is omega measured in? And what is alpha measured in? So theta is going to be measured in a new set of units that you may or may not have heard of before, and these are called radians. and omega will be in radians per second. Whoops. We sometimes denote it as rad per second. And alpha is going to be rad per second squared. Okay, radians per second squared. Now, radians actually technically are a unitless measure. Okay, so when you are multiplying through in things, radians technically don't get a measurement. And we'll see how that works later on. But for now, this is what we work with. So what is 1 radian? So 1 radian is equal to the angle at which the arc length of a circle, we denote that by the letter S, equals the radius. Okay, so in picture form, which is a little bit easier to conceptualize than that statement right there, right? So I have another circle, and I have a radius r, and again I start on the x-axis, and if I start at the x-axis and move up some distance here, okay, we call this the arc length S, right? And the point at which, if I were to unstretch this arc length and measure it, and that measurement would be equal to the radius, that particular angle right there is equal to 1 radian. Okay, so if I were to take S out, or I should say the angle that, if I were to make a measurement of S, stretch it out, and it be equal to R, then that is equal to 1 radian. And it happens to be uniform for all circles, so 1 radian is very close to 57.3 degrees. Okay, so 1 radian is about 57.3 degrees. And in a circle, right, just for your information, if I were to start at the x-axis and go up here, then I've subtended an angle of pi half radians. And if I go halfway around the circle, then I've gone pi radians. And if I go all the way around the circle, you may have guessed that this should be 2 pi. And that's actually where the formula for the circumference comes from. The circumference of a circle is equal to 2 pi r, where c is the complete distance around the circle, and let me just clean that up. 2 pi is the angular distance around the circle, and r is the radius. Okay, so 2 pi radians is the angle all the way around the circle. All right, so we can do a couple of examples here real quick, and let's just say that we have an object moving on a circle, and it starts at the origin, or I'm sorry, it starts on the x-axis. The origin is here. Our object starts on the x-axis at t equals 0 and goes up to an angle of 1 radian at a time t 1 second. Okay? What is the angular velocity? Okay? So the angular velocity is just going to be the change in angle over the time. And our change in angle, well, we started down here, and when we go up here we measure the angle. It turned out to be 1 radian. Divided by our time interval, well, our stopwatch started at 0 and we stopped it at 1 second, so this is 1 second. So our angular velocity here is going to be 1 radian per second. Okay? Okay, so now let's look at another example. Let's suppose this time we have a merry-go-round. Okay, so we have a merry-go-round with some kids on it. And it's being accelerated at a rate of 0.005 revolutions per second squared. Now a revolution, okay, is just 2 pi radians, so sometimes angles are measured in revolutions as opposed to radians. But 1 revolution is just obviously 1 full circle, or 1 full rotation around. Okay, so nothing too obscure there. All right, and let's say that it starts from rest, so omega initial is 0, and after 1 minute we want to know through how many revolutions our merry-go-round has gone through. Now, because both of our angular units are in revolutions here, our final angular measure is going to also be in revolutions, so we don't need to do any converting. But just for your sake, right, 1 rev is equal to 2 pi radians, right? So if you ever needed to convert between the two, that's the conversion factor. 1 revolution is equal to 2 pi radians. So how do we do this? Well, we know that we have an equation. We can go back several slides, but I won't flip through them all. But we can just remind ourselves that we have an equation that relates velocities, times, and accelerations. And so we're given that our initial velocity is 0, so this term goes away. We're given an angular acceleration, and we're given our time. Now, our acceleration is given in revolutions per second squared, and our time is given in 1 minute. So we're going to want to convert one of those two over. I highly recommend you convert your time from minutes to seconds. It'd be a bit of a pain to convert the second squared, 1 over second squared, into 1 over minute squared. So if we do so, then we're going to have t is equal to 1 minute, and of course in 1 minute there's 60 seconds. And our equation is now going to read, because we were able to drop out this term, it went away, so we're just left with the 1/2 alpha t squared, which is just going to be 1/2 times 0.005 revs per second squared times our time of 60 seconds squared. So this is going to be 1/2 times 0.005 times 3600 square seconds. That's what 60 squared is. And of course our seconds squared are going to cancel out. And if you run this through your calculator, okay, half of 3600 is going to be 1800, and multiplying by 0.005 is like multiplying by a half and then, multiplying by a half and then dividing by 100. And so if you do that, right, half of 3600 is 1800. Another half of that is 900, and then you divide that by another 100 and you come up with 9 revolutions. So in the 1 minute, the merry-go-round only went through 9 revolutions. Not very much. So this merry-go-round was not going very fast at all. Probably for a toddler or somebody like that. Okay, but that gives you a bit of a sense on how to use some of these equations. In the next video, we'll start to look at torque, and we will see you then.